Hello everyone and welcome to my presentation. I'm Jarin and today I'm excited to share our work titled Enhancing Real-Time Decision Making with Scalable, Safe and Private LLMOps and Context-Aware RAG Workflows. This project was a collaborative effort with Jeremy Farrett and Nidish Kumar Pilla at Mind in a Box. We developed a system that integrates robust large language model operations with advanced retrieval augmented generation to improve the relevance and efficiency of AI decision making in high-stakes environments. Over the next few slides, I'll guide you through our motivation, methodology, results, and the future directions. Let's begin by looking at the motivation behind our work. Large language models have revolutionized AI by offering impressive generative capabilities, yet they face a significant challenge. They rely on static pre-trained knowledge. In rapidly evolving fields or high-stakes applications such as legal, medical, or financial decision making, outdated or insufficient context can lead to errors or suboptimal decisions. Our goal was to create a system that overcomes this limitation. We needed a way to supply LLMs with fresh, domain-specific context in real time. That's where retrieval augmented generation or RAG comes in. By dynamically retrieving and incorporating relevant external information, RAG helps ensure that AI responses are both accurate and contextually relevant. Our approach integrates scalable LLMOps with advanced RAG workflows to achieve this, while also prioritizing data privacy and operational safety. Let's dive deep into retrieval methods. Here we explore how retrieval strategies power RAG systems. First, keyword-based search relies on exact matches. It is fast and transparent but struggles with queries where semantic understanding is necessary. Dense search, on the other hand, uses neural embeddings to capture semantic meaning. It is powerful for context but demands heavy compute. Hybrid search merges the best of both worlds. It ranks documents using a mix of semantic relevance and keyword overlap. This balance makes the hybrid ideal for real-world applications where precision and recall matters. The next retrieval strategy is re-ranking. Here, first we cast a wide net. Using a fast retrieval method like dense vector search or keyword matching, we fetch a broad set of candidate documents. This step prioritizes speed, ensuring we don't miss potentially relevant results. Next, we refine. A cross-encoder model scores each query document pair, comparing them deeply for semantic relevance. Unlike the initial retrieval, this step is slower but far more accurate. Finally, we filter, keeping only the top scoring 5 or 10 documents after re-ranking ensures we deliver the most relevant results. Hide or hypothetical document embeddings is a clever retrieval strategy. Instead of searching directly with the user's query, we first ask an LLM to imagine an ideal answer. This hypothetical document becomes our North Star for retrieval. This is because real queries are often vague and don't match the corpus. Hide bridges this gap, transforming, say, a messy question like, how does climate affect crops, into a structured, search-friendly passage that guides retrieval. Off-the-shelf embedding models struggle in specialized domains due to a lack of domain-specific knowledge. Instead of costly retraining, a lightweight transformation layer adjusts generic query embeddings to align with domain knowledge. This involves a single D by D projection matrix trained with a triplet loss to improve retrieval by bringing relevant documents closer while pushing irrelevant ones away. This approach is fast, cost-effective, and enhances domain-specific search. Now let's look at experiment setup and methodology. Let's take a deeper dive into our system architecture. Our Mind-in-a-Box solution is built to operate under two distinct deployment scenarios, which are illustrated in the two figures. The first one is the on-premises modality, which is shown in the figure on top. In this deployment, we leverage the Mind-in-a-Box Catalyst system for LLMOps, coupled with the Mind-in-a-Box Sense system for data operations. This figure represents our fully on-premises architecture, where all components, including the GPU cluster, LLM inference server, vector embeddings, and ranking systems, are housed within our infrastructure. This setup ensures full data privacy and control, which is crucial for organizations handling sensitive information. The Box Catalyst server is powered by NVIDIA A30 GPUs, which provide accelerated inference for LLM-based tasks. Kubernetes orchestrates model deployment, ensuring scalability and efficient workload distribution. The VLLM inference server plays a crucial role in delivering low latency performance. The Box Send Data Ops server hosts vector embeddings and BM25 ranking to enhance search and retrieval performance within our proprietary database. The next one is hybrid modality, which is shown in the figure on bottom. This figure shows the hybrid workflow where our system integrates with external LLM platforms like OpenAI's LLM API. Unlike the on-premises model, this approach allows us to extend compute capabilities beyond our infrastructure, ensuring greater flexibility. As you can see, there is an LLM application layer. This is where the retrieval augmented generation is performed, which bridges the gap between our vector search capabilities and the external LLM inference. Then you can see the Box Send Data Ops server, which even in a hybrid setup, we maintain control over the vector embedding and BM25 ranking processes, ensuring optimized retrieval before handing off requests to cloud-based LLMs. The external LLM integration provides additional scalability, allowing us to offload workloads when necessary. To validate our approach, we selected the SciFact dataset, a benchmark designed for scientific claim verification. Its structure mirrors real-world tasks where accuracy and relevance are non-negotiable. When evaluating retrieval systems, we must measure both what we retrieve and how will we retrieve it. Let's break down the key metrics that define retrieval quality. The first one is NDCG, or Normalized Discounted Cumulative Gain. This ensures that the most relevant documents appear at the top of ranked list. This metric assesses both relevance and ranking quality. The next one is MAP, or Mean Average Precision. It balances the precision and recall across the entire result set. It penalizes systems that fail to surface relevant documents earlier in the list, providing a more holistic measure of the retrieval effectiveness. The next one is recall. It measures whether all relevant documents appear in the top care results. In critical domains like healthcare, missing even a single document can have severe consequences. The next one is hit rate. It quantifies the probability that at least one relevant document appears in the top results. This metric is crucial for ensuring user satisfaction, as users expect to find useful information quickly. The next one is MRR, or Mean Reciprocal Rank. It evaluates how quickly the first relevant result appears. This is particularly important for real-time applications where response speed is critical. Beyond retrieval quality, system efficiency determines whether an LLM can operate at scale. Throughput measures the number of requests per second the system can handle and the number of tokens processed, defining the scalability of the inference system. For latency, three key metrics impact user experience. The first one is time to first token, or TTFT. It measures how quickly the model starts generating a response. The next one is TPOT, or time per output token. It evaluates the efficiency of token generation, impacting real-time usability. The next one is inter-token latency, or ITL. This determines consistency in response generation under sustainable load. By tracking both retrieval quality and inference efficiency, we ensure that LLM-powered applications deliver accurate, complete, and fast responses, making them truly usable in real-world scenarios. We started transforming the SciFact corpus into structured LangChain documents, making sure the data was clean and standardized for optimal processing. Once the data was done, we indexed everything in OpenSearch using a dual approach: BM25 for keyword-based retrieval and vector embeddings for semantic search. This gave us both traditional matching and a deeper meaning-based understanding of the content. To make retrieval more effective, we built our pipeline in stages. First, we started with baseline retrieval using BM25 for sparse retrieval and BAS BGE small English model for dense embeddings. This gave us a solid foundation to build on. Then we took things a step further with hybrid retrieval combining BM25 and dense embeddings. This gave us the best of both worlds, keyword precision and semantic relevance. But we didn't stop there. We added re-ranking with flash rank, which helped reorder the top 50 documents, making sure the best results surfaced first. We also leveraged high-day or hypothetical document embeddings using GPT-4o Mini to generate synthetic queries that mimic how real evidence appears in documents. Finally, we fine-tuned embeddings for scientific claims with a lightweight adapter trained using triplet flows rather than retraining a full model, which saved time and resources. To evaluate how well the system performed, we focused on two main things: retrieval effectiveness and system resilience. We checked whether we were retrieving all relevant documents with recall and assessed ranking quality using NDCG map and MRR. And because a system like this needs to perform well under real-world conditions, we stress tested it using shared GPT dataset, simulating bursts of traffic to see how it held up under load. With this structured approach, we built a retrieval pipeline that's not just accurate but also scalable. Now let's take a look at results and conclusion. After running extensive experiments, we now have a clear picture of how different retrieval methods stack up. First, recall performance. It tells us how well we retrieve all documents. The adapter enhanced method led the way, achieving 0.76 recall at cutoff 2, a 43% improvement over BM25. Meanwhile, Heyday excelled at broader retrieval, hitting 0.91 recall at cutoff 10, but with a trade-off. It struggled in ranking sensitive metrics like NDCG. Speaking of ranking quality, the adapter enhanced method outperformed standard dense retrieval, reaching 0.75 NDCG at cutoff 2. Our hybrid approach showed some gains, but there is still room for optimization. Overall, the adapter method proves to be the best all-round performer, while Hida is great for broad recall. With further tuning, we can refine hybrid approaches to unlock even more potential. Our system scales well in two key areas: throughput and latency. First, throughput. We can handle about 7.25 requests per second, processing nearly 1,700 input tokens and 1,400 output tokens per second. This makes it great for high volume tasks like bulk document processing. Now, for latency, most responses start within 41 seconds, but in rare cases, complex queries push that up to 104 seconds. Token generation is generally smooth with a 151 millisecond median, though we see occasional spikes. Overall performance is strong, but with some fine-tuning we can make responses even faster and more consistent, especially for real-time applications. We are honored to be the LLMOps backbone for Galicia, a prestigious EU-backed project under the NGA Circular program. We provide open source LLMs with full OpenAI API compatibility, ensuring seamless integration for researchers and developers. Our end-to-end infrastructure support allows Galicia to focus on generating and validating code using AI without worrying about operational complexities. In conclusion, our work bridges the gap between scalable LLMOps and precise retrieval, delivering a robust solution for high-stakes decision-making. By integrating Hide for comprehensive recall and adapters for precision, we achieve significant improvements over traditional methods. While throughput metrics validate scalability, latency remains a challenge for real-time use. Future efforts will focus on optimizing response times and expand into new domains, ensuring our framework remains at the forefront of secure, efficient AI systems. Thank you all for listening.